Alright, so today's lesson is Unit 2, so in dynamics still, and we're going to learn about gravitational force today. So we have talked about before the gravitational acceleration or acceleration due to gravity, which we labeled that acceleration, if you remember, to be 9.81 meters per second squared down. Okay. Now, today we're going to talk about the force of gravity. And the force of gravity we label F subscript g, and it is a vector. So we have the vector symbol above it. And in this equation we have it equal to mass times this other g. Now that g in our first unit we sometimes labeled A as simply g, right, as 9.81 meters per second squared. But we can write it with slightly different units, equivalent units, but slightly different units. We're going to write it as 9.81 newtons per kilogram. Now, a newton per kilogram is the exact equivalent unit of a meters per second squared. But in this unit, in this chapter, I should say, in this chapter, we are going to be using these units, and I'm going to refer to this as the gravitational field strength. So try to imagine this. So we have the Earth. Draw the Earth here. There's the Earth. And all around the Earth, there's this invisible field that is pointing towards the Earth. This is called a gravitational field. And anything inside this field, or anything that has mass that is inside this field, will feel a gravitational force towards the Earth. And the strength of that field depends where you are. If you're on the surface of the Earth, the strength of that field is 9.8 newtons for every kilogram of mass. And we can calculate the force that acts on you by simply taking your mass and multiplying it by 9.81 newtons per kilogram. Now, before I go any further, I do want to make sure we properly define mass versus weight. Now, in English, we use these two terms interchangeable, but in physics, they do not mean the same thing. Mass, which you probably first learned in a chemistry course, is just the amount of matter, okay, or stuff. And so you can say, I don't know, this coffee. Now in English we say this coffee weighs 100 grams. But that sentence is incorrect in physics. Right? We would have to say the mass of this coffee is 100 grams. Because weight means something else. Weight is the force of gravity that acts on mass. And so weight is properly measured in newtons. It's kind of confusing because everywhere you go, you can go for a checkup at the doctor and they'll say, okay, let's just stand here, we're going to check your weight. But really they're not checking your weight, they're checking your mass. Weight is measured in newtons. And we can do this on the first problem here. If you want to figure out exactly what your weight is, then you would take your mass and multiply it by 9.8. I'm going to do it for a theoretical student in a classroom at Huron Heights. Currently, there's nobody in this classroom. But our student has a mass of 60 kilograms. See, it's so ingrained in the English language to say weighs. So to calculate the weight, when it says weight, we're actually going to calculate that force of gravity that acts on the student. So in this case, it is m mass times that gravitational field strength. So 60 kilograms times 9.81 newtons per kilogram. So when we do that on our calculator, we get 588.6, but taking to proper significant digits, I'm going to round that to 590 newtons. So the student's weight is 590 newtons. So something else I wanted to talk about, the difference between mass and weight. Let's say you were to take a vacation, and this is the future, so we're going to take a vacation to the moon. It'd be a great vacation. I'd love to take that vacation. So as you go from here to moon, currently it's about a 3-day trip, but who knows? Maybe in the future it'll be less. But as you go from here to the moon, your mass won't change. Or it won't change extremely little. It might change on the order of a few grams, but it's not going to change. However, your weight will change a great deal because the gravitational field strength on the moon is not 9.81, it's 1.6 newtons per kilogram on the moon. That's about 1/6 of what it is here. So your weight would be 1/6 of your weight on Earth. Your weight changes, but your mass does not. So don't think of it as if like, hey, I just went to the moon, like best weight loss program ever, right? In that case, yeah, it is a great weight loss program, but it's not a great mass loss program. Okay, so it is going to be tricky, but I'll remind you over and over and over again the difference between mass and weight so that we can sort of remove our preconceptions that due to the English language they are the same thing, because they are not. Okay, so we do talk about newtons a lot. Now usually when we're in class, and maybe when I do have you guys here in a few weeks, we'll actually test it. So there are these things called Newton's scales, which I do have one here. This looks like this. It's also called a spring scale because it uses a spring inside of it. And you can just put something on it, test its weight, and it will go down, and you can figure out its weight in newtons. Okay. But again, you can always just, if you know the object's mass, you can calculate the weight. Next, I want to talk about free fall. Now, free fall is a term that we use to illustrate that the only force that acts on an object is gravity. So no other force is acting on an object. So, I mean, if you were parachuting, jump out of a plane and go parachuting, you have a large drag force upwards. So it's technically not free fall. Although, again, in the English language, we tend to call it that. So what would be a case of free fall? Well, let's ignore air resistance. Let's go on a ride in an elevator. So if you go in an elevator, what you want to do is bring a scale for yourself to stand on. Great. Now, if you stand on that scale, let's say your weight is, for example, 600 newtons. If the elevator were to drop, I don't know, maybe you were going on one of those drop zone type of elevator rides or Tower of Terror or something like that, and the elevator dropped, that scale would read 0. And the reason why that scale would be reading 0 is because the scale and you are both falling at the same rate. Right? Now, a scale actually, if you were standing on the scale and it reads 600 newtons, if I were to draw a free body diagram for that, there would be a force of gravity acting on you, and there would be a normal force pushing up, which is the springs in the scale pushing back on you. Now, when you fall, there's no more normal force. There's only gravity. So you can say both you and the scale are in free fall, but the scale is actually measuring that normal force. And since it's not anymore, it's going to read 0. Let me just pause. Okay, a couple other terms I want to go over first is one is net force. So we talked about net force yesterday and we calculated net force. But then we can have a balanced net force. A balanced net force is when all the forces on an object add to 0. When that happens, we say the forces are balanced and we don't see any change in motion. So for example, if we go back to over here, where you're standing on the scale, initially, if you're standing on the scale, we had our normal force up and our gravitational force down, and those forces were equal, and therefore the net force on you is balanced, and there's no change in your motion. You're just standing on the scale. It's not until the elevator drops where we remove that normal force and you start accelerating down. Next thing, terminal velocity. So let's say you're going skydiving. You jump out of a plane. What happens is this isn't free fall because there's air resistance acting on you. So initially when you jump out of a plane, you have the force of gravity acting down. And because you're not going very fast yet, you have a very small amount of air resistance. I'm going to write that as FD for drag. Now that's not a balanced net force. So since the greater force is down, we accelerate down and we start going faster and faster and faster. The faster you move, the greater that the surrounding air pushes up against you. And so that force becomes bigger. Still, gravity is larger than that, so you move faster and faster and faster, and eventually you'll reach a point where that drag force is the same size as your force of gravity down, and now you have a balanced net force, meaning your motion no longer changes. Doesn't mean you stop moving. You don't suddenly stop and start levitating like Superman or anything. It's just your motion doesn't change anymore. So you've reached what we call terminal velocity. That's the maximum speed an object falling due to gravity can reach due to air resistance. And different things reach terminal velocity at different points depending on your mass and the exposed surface area, which is why sometimes in movies when you see people skydiving, sometimes they like go completely vertical like that to go faster. Sometimes they open up like that to go slightly slower. Then of course you have your parachute. Parachute is very important. Okay? That'll make sure you have a nice low terminal velocity for when you reach the ground. Last thing I want to talk about are astronauts on the International Space Station. So I'm sure at some point we've all seen videos or images of astronauts on the International Space Station, and they're floating around. Okay, well, here's my question. And just think about this for a second. If they're floating around, does that mean there is no force of gravity acting on them? So when you're on the space station, you're floating around. Okay. But what about this person back on the elevator? When the elevator's falling, until it hits the ground, it seems like that person is just floating around. They are essentially weightless. In fact, even the scale reads a weight of 0. But are they truly weightless? Is there no force of gravity acting on them? Well, no, that's not true. Right? We have this force of gravity acting on him right there. That's why he's accelerating down. But yet he feels weightless because he's floating around in the elevator. Well, what about people on the International Space Station? Now, they're much further away from the Earth. So, no, the gravitational field strength for them, or the value of G, would not be 9.8. In fact, the value of G for the ISS, for astronauts on the ISS, is 8.7. So it's definitely not 0. It's 8.7 newtons per kilogram. It's very close to 9.8. In fact, there's quite a lot of gravity acting on them. So they're not weightless but they certainly appear to be weightless. And the reason for that is they are in free fall. The only force acting on them is gravity, and so they're falling. They're accelerating downwards at this point, 8.7 meters per second squared, which is very close to what we would feel if we just dropped something on the Earth. Okay, that probably brings up more questions than answers, because then it's like, wait a minute, if they're always falling, why don't they crash into the surface of the Earth? And this was an idea that Newton thought of quite a while ago. Let me just this is called Newton's cannon. So he imagined a huge cannon on top of a mountain. And if you were to shoot a cannonball, it would do this and hit the Earth. So it does come down and hit the Earth, but look at the path it makes, the trajectory. It does go part way around the Earth before it hits the Earth. So if we can figure out a way to increase the speed of that cannonball, then it would go further around the Earth and eventually crash here. And if you can keep increasing the speed of the cannonball, eventually it would go all the way around the Earth. And it would be constantly falling towards the Earth, but the only reason it doesn't actually fall down is because as it falls towards the Earth curves away from it. I mean, look at this. Here's the cannonball, shoots from a position here. The ground is right there at that position, at that height right here. But it hits the ground here, not here. It's because the ground curved away from it. And so astronauts on the ISS are always falling, they're just never falling down because the Earth curves away from it. And it's the same for if you have an asteroid or that's coming in for a close path, the Earth will sort of bend its path, and yes, it will be falling towards the Earth because it will feel that gravitational attraction of gravity to the Earth, but because it's moving so fast, right, it doesn't fall. The Earth curves away from it, and it doesn't hit the Earth, and it just moves outwards. So it's the same thing. You would need to shoot a cannonball extremely fast, maybe around 10 kilometers per second. So if you can shoot a cannonball, and don't do this in the Earth's atmosphere because then the friction of the air would just cause that cannonball to be a fireball. But if you can go up above the atmosphere where there's no more drag or air resistance and shoot that cannonball at about 10 kilometers per second, its speed will be so fast that as it falls towards the Earth will curve away from it. Okay, I think I've repeated myself about 5 times there, so I'm going to stop and see if anyone has any questions. Okay, in our next sample problem, here we have a 60 kilogram person standing on a bathroom scale calibrated in newtons. A friend pushes down on the person with a force of 72 newtons. What's the reading of the scale? Let's draw a free body diagram. Every time we do forces questions, we're going to start with a free body diagram and write all the forces acting on that person. So we have the force of gravity. We have an applied force, thanks to the friend pushing down. And then since you're standing on the scale, we have that opposite perpendicular contact force that we call the normal force. And the normal force is what's going to be the reading on the scale. So that is actually what we're trying to solve. Now, since the person is just standing there, their motion is not changing, we can say that they are in equilibrium or all their forces are balanced. So we would say that the net force equals 0. Okay, so now we just need to add all of our forces, which are all vectors. And I'm going to choose up to be our positive direction. So let's write all of our forces first. We have the net force, sorry, not the net force, the normal force. We have the applied force, and we have our force of gravity. And that all equals 0. So normal force is what we're looking for. The applied force is 72 newtons down. So I need to make that negative, so negative 72 newtons. I don't know why I wrote a 0 there. Okay, and gravity is also down, so that's going to be negative, and we calculate it using mass times gravity. We actually did it up in this question above, where 60 kilograms times 9.81 is 590 newtons, but I rounded that answer, so let me just put it in again so we don't round. So 60 kilograms times by 9.81 newtons per kilogram all equals 0. So these terms I can bring to the other side of the equation. They'll become positive, and we'll get Fn equals 72 plus 60 times 9.8, so 72 newtons plus, and 60 times 9.8 without rounding to 590 is 589. I'm still rounding, but I'm doing it just an extra significant digit. And that equals 661 newtons. Okay, so that's what the scale would read.